Hello everyone, this is lecture 12, Newton's divided differences. So in this lecture, we're going to investigate divided differences to fit a low order polynomial to a set of data points. So in the last lecture, lecture 11, we look at high order polynomial functions, even though the example in the lecture notes focus on just polynomial of degree 2, polynomial of degree 3, so on and so forth. But the more data you have, the higher the degree of the polynomial is going to be. Now, the focus of this lecture is that if you have more data point, even if you have more data point, can you still fit a low order polynomial function or polynomial function of low degree, like quadratic or cubic functions, right? So for example, if we have this data set, right? So you have 10 data points on the plot here. And of course, you can use high order polynomial function. That is, so you have 10 data point, you need a polynomial function of degree 9 to fit the data point. Now, can you actually fit a quadratic polynomial or a cubic functions in for this 10 data point, right? So this straight line here is the quadratic polynomial. So it's not really going through all the points, but it's fit into those 10 points, right? Just give you some idea of how the data behave and hopefully make a kind of a predictions for later data points. Okay, so that's the idea for this lecture, right? So fit a polynomial of low order degree, regardless of the number of data points, right? Even though you have a lot of points, still can you fit a low order degree polynomial functions to the data point, right? Of course, again, the number of data point exists the number of constant necessary to determine the polynomial, right? So 10 data points. If you use quadratic function, then you just have A0, A1, and A2. Those are the number of constant, right? So 3 constants, 2 for you to find. And of course, the low order polynomial generally will not pass through all the data points. That makes sense, right? And this process is called the smoothing process because you smooth out all the curvy or oscillations thing here if you use the 9 order polynomial. Okay. So that's, of course, there's the advantage and disadvantages using the low order polynomial functions, and you will explore that in this lecture, right? So one thing that you can think about low order polynomial function is that you can do derivative, you can do integral fairly easily, right? If you have higher order polynomials, those things become a little bit more difficult to deal with, okay? So when you do this smoothing process, that means choose low order polynomial functions for a lot of data points, you need to even consider two things at the beginning that should we actually use a polynomial to begin with, right? And you will see that in the last lecture that you have a data set, you try to do some calculation and you discard or you draw a conclusion that a polynomial should not be used, right? Right. So the very first question, should I use a polynomial function to fit this data set, right? Now, if let's say, yes, you can use a polynomial function to fit the data set, then what order should the polynomial could be, right? So that's the two questions that we need to answer. Should we use polynomial functions and should what order the polynomial should be, right? Or what degree of polynomial function should be. So the process of smoothing requires two decisions. The order of interpolating a polynomial must be selected, right? So, you choose quadratic, which is degree 2, or you use cubic function, which is polynomial of degree 3, so on and so forth, right? And the coefficients of polynomial function must be determined according to some criterion for the best fitting polynomial, right? So you can use Chebyshev criterion, you can use least square criterion to calculate the the coefficient of the polynomial. Okay, so in this lecture, we just going to answer the two questions that we have here. Should we use polynomial functions? And in what order should the polynomial functions going to be, right? And we're not trying to solve the value of the coefficient in the polynomial at all. We're just going to set up the problem such that we can answer these two questions. Okay, and the particular technique that we use to answer this two questions is called Newton's divided differences. Okay, so let's start with a quadratic functions, right? So a quadratic function is of the form a plus bx plus cx, where and one condition in this case that c has to be different from 0, because when c is equal to 0, then we have a linear function, so there's nothing to do there. The good thing about the quadratic function is that when you take the derivative, so this is where I assume the knowledge of calculus, right? When you take the derivative of the functions, right, so the first derivative is going to be, right, so derivative of a is 0, the derivative of bx is going to be b, and the derivative of cx squared is 2 cx. Then the second derivative of the function is 2c, right? Because the derivative of b is 0, and the derivative of 2cx is 2c. Now, if you take the third derivative, let me fix this a little bit. So the second derivative, third derivative, you get 0, right? So when you take the derivative of this, right, you recognize that for quadratic functions, the second derivative is a constant, right? So 2c is a constant. And the third derivative is going to be equal to 0, right? And we're going to use this fact for later calculations because, right, you find later on you're going to do divided differences, and you will see that, okay, I have one column which is a bunch of constant and repeated constant, right? And then the next column is going to be a bunch of 0. Then it give me the conclusion, give me the idea that, okay, I should use this particular polynomial function of this particular degree. Okay, it will make a little bit more sense later on when you go into a data set to work with the data sets, right? So the motivations that I want to give here is that when you have a polynomial function, especially in this case, the quadratic functions, the second derivative is a constant and the third derivative is a 0. So keep that in mind. However, right, when we consider this particular functions, we take the derivative, we assume all the data points are continuous, right? Or rather, the function is a continuous function. But in reality, we don't have continuous data points. We have discrete data points, right? Because let's say you want to measure the temperature of a coffee cup, of a hot coffee cup. You don't take the temperature for every nanosecond or every picosecond, right? You take the temperature of the hot coffee cup every like 1 minute or 2 minutes, right? So those data points are discrete data point. We don't have that luxury of continuous functions, right? So let's quickly know that this is for continuous functions. And we only have discrete data point. Okay, so what should we do? Right. So we go back to the idea that we learned in calculus 1, which is the definitions of derivative, right? Another way to express the derivative besides taking prime is dy dx, right? So derivative of y with respect to x, right? And we learned that the definitions of the derivative is that the change in y over the change in x and you take the limit at the chain in X approaches 0. So we're going to use this idea, right? What we're going to do is we're going to calculate the change in Y, and then later on doing the change in X, right? And then you do that divisions. That is called the divided differences. That's the idea. Okay, so with that idea, let me go through an example here so that I set up the change in Y first, and then later on get some explanation and forward that to doing the divided differences, right? So in this case, we have a curve called y equal to x, where is the quadratic function or parabola. Right, so pass it through this point is obviously that you let 0 into x equal to 0, then of course y equal to 0, x equal to 2, y equal to 4, x equal to 4, y equal to 16, so on and so forth. That makes sense. Now let's do a quick calculations here for the differences. Okay, so I'm gonna write D1. That means the first differences, right? That means just the difference between the y values, right? So 4 minus 0 is going to be 4. 16 minus 4 is going to be equal to 12, right? 36 minus 16 is going to be 20. And 64 minus 36 is 28. All right. So that's the first difference, right? The first difference is calculated from taking the difference between two data, two output, two consecutive outputs of the functions. Now for the second differences, right? So I'm going to call that D2. What I'm going to do is I'm going to find the difference between D1, right? So 12 minus 4 give me 8. Now 20 minus 12 give me 8 as well. And 28 minus 20 give me 8 as well. Right, so the second differences are just constant. Okay, good. Now the third differences, that means you want to find differences between D2. Right? So 8 minus 8 going to give me 0. And 8 minus a here give me another 0. Okay, so just for the sanity of the calculation, let's do D4. So of course 0 minus 0 is 0. All right, so this table of that you just done with the calculations tell you a few things. That the second differences are constants. So the second differences are constants, or rather repeated constant, right? So constant means there's no change, there's no differences in the number, right? So you have 8, 8, 8 here. And you make another observations that the third differences are 0. All right, so it's aligned with what we have seen here when you do the derivative for continuous functions, right? The data point that you have is calculated from this quadratic functions, or the function of power 2. So it's also say that, okay, the second derivative is a constant and the third derivative is a 0. Here corresponding to the discrete data point, the second difference is constant, so there's no change in the number here, and the third differences are 0, so they align between the continuous values and the discrete value that you calculate, right? Another, however, right? Even if the data are essentially quadratic in nature, right? You can like a bunch of data and it's behaved like a quadratic functions. We cannot, or we could not expect the differences to go to zero precisely. It's very, so this is a very precise calculations to give you zero in the third differences and the fourth differences. In reality, we don't have that luxury to know the type of functions we have at the beginning, right? And we expect that to behave like a quadratic function. The differences will not go to zero precisely, right? But we might expect the data to become smaller and smaller when you do the differences. Okay, so we say that even if the data are essentially quadratic in nature, we would not expect the differences to go to zero precisely, right? But we might expect the differences to get smaller. All right. And we can make the differences even smaller by using this particular formula right here, delta y over delta x. And so we can make the differences smaller by computing divided differences. So it's a highlight here. So divided differences. All right, so I'm just say that we base on this idea, right? And this particular formula is going to be the same for the first divided difference, right? So the first divided difference is calculated as y2 minus y1 over x2 minus x1. So if anyone who has taken pre-calculus, calculus sequence, you know for sure this is the slope of the secant line go through 2 points, right? So, or the slope of the line going through 2 points. All right, so let me quickly note that here you have the graph, and this curve going through 2 point x1, y1, and x2, y2. And if you draw a straight line going through this 2 points, then you can actually calculate the slope of that line, right? So here you calculate delta y equal to y2 minus y1. This is the change in y. And for delta x equal to x2 minus x1, you have change in x. All right. And a quick note here is that the first divided difference is the slope of the line through 2 points, right? Through x1, y1, and x2, y2. Okay, so that's the first divided difference. Now the second divided difference is calculated as follow. It's equal to y3 minus y2 over x3 minus x2 minus y2 minus y1 over x2 minus x1 all together. divided by x3 minus x1. All right. So it's get more complicated as you go further away. Right? When you calculate the second divided differences, the third divided differences, so on and so forth. Right? You have to use the knowledge that you have in the previous divided differences to do the calculation for the next divided differences. Okay. And this divided difference, or the second divided difference, so the second divided difference is equal to, or essentially, the difference between the adjacent slopes divided by the length of the interval over which the change has taken place. Okay, so going through x1, y1, and x2, y2, you can calculate the slope. Now, the line going through x2, y2, and x3, y3, you can calculate the slope. Now, you want to know what is going to be the changes or the divided difference happen between x1 and x3, then you can use the second divided difference, and so on and so forth, right? So you can do, you can extend that to the interval between x1 and x4, x1 and x5, so on and so forth. So the formula, I'm just going to give it to the second divided difference because it's getting more complicated as we go further away. In practice, what we're going to do is we're just going to do using the Excel spreadsheet to help with our calculations. All right. Before I go to the Excel file, I'm going to do this by hand quickly, and then I will show you how to do the calculations in Excel. All right, so data, one side you have the data, and on the other side you have divided differences. All right, so I'm gonna do 3 divided differences, right? The first divided difference, again, the change in y, so 4 minus 0 divided by the change in x, so 2 minus 0, so 4 over 2 equal to 2. Now the next divided difference, or in the next data point, you have 16 minus 4 divided by 4 minus 2. So you're going to have 12 divided by 2. You have 6, right? So on and so forth. So 20 divided by 2, you have 10. And 28 divided by 2, you have 14, right? 28, why? Because 64 minus 36, you have 28. And 8 minus 6, you have 2. Therefore, 14 is the divided difference for the last 2 data points. Now, for the second divided difference, what you do is that you take the difference of the first divided difference, right? So 6 minus 2, and you divide it by the change that take place in the interval. So from 4 to 0. So 4 minus 0 is going to be equal to 1, right? Now for the next 2 values, so you do 10 minus 6 divided by 6 minus 2, right, is going to be equal to 1 as well. And the last 2 data, that's 2 first divided difference. You have 14 divided by 10 over, right? So 8 and divided minus 4. And it's going to be equal to 1 as well. Okay, So now for the second divided difference, you have constant, right, which aligned with what we have here, right? The second derivative of a quadratic function is equal to a constant. All right, so the third divided difference is going to be 1 minus 1, right? So take these two informations divided by the change that, or divided by the length of the interval over which the change has taken place, right? So the change taken place here, so 6 minus 0. So 0 over 6 going to be equal to 0. And for the next two numbers, you have 1 minus 1 divided by 8 minus 2. 0 over 6 or equal to 0, right? So doing this calculation, you see that the divided difference, the second divided difference is a constant. So that is, there's no change in the number here. And the divided difference, the third divided difference is equal to 0. So suggests that we should actually consider a quadratic function or polynomial function of degree 2 to fit the data set that we have. Okay, so there's so much that we can do calculations by hand. Let me go to the Excel file to help us with the calculations, because of course, in the real world situation, you have millions of data points and you don't want to do everything by hand. Okay, so let me turn to Excel. All right, so here's the setup. On the left-hand side, you have the lecture note, and on the right-hand side is the Excel file. So let me do the calculation for the first example. Right? So in the first example, you want to calculate the differences, not the divided differences, right? Just the differences. Okay, so the first difference, let me center this, is equal to the change in y, right? So you just drag the information down to here. Then the second differences is equal to 12 minus 4 here. And you drag the formula down, and you can see that the second difference is aligned with what we have in the note. And for the third difference, you have this is equal to 8 minus 8. Drag the formula down, and for the insanity of the calculations, I'm gonna take this minus this. So this is the first example. So let me change this to example 1 that we have in the notes, right? So this help us do the calculation for the differences. Now, I'm gonna use the same data set, right, to do the divided differences, because you want to make the differences smaller, right? So I'm open another tab, change this to example 2, and I'm going to my second example. So I'm just going to copy and paste the data here. All right, so the first divided difference is equal to, right, the change in y over the change in x. And you just drag the formula down up to this point, right? So you have 2, 6, 10, 14. Now the second difference is going to be equal to, right, the change in the first divided difference divided by the length of the interval where the change has taken place. So 4 minus 0. Right. Then just drag the formula down, and you have the second differences to be 1. And for the third differences is equal to the change in the second divided differences divided by the length of the interval where the change has taken place. Okay, drag the formula down, right? And of course, for the insanity of the calculation, you do the fourth divided difference, right? So the change in the third divided difference divided by the length of the interval where the change occur. All right, so you have this table for the second example. Now we're gonna go to the third example, right? With the knowledge that we have on divided differences, right? We still want to go back to this particular idea, right? Should we use a polynomial or function to begin with to fit the set of data points, right? And yes, so if you want to, if you use a polynomial function in one order of polynomial or one degree of polynomial functions, that would be appropriate for you to use. All right, so let's do example 3. So this is the data set, right? The idea of this example is that to collect data on the tape recorder and with its elapsed playing time, suppose we are unable to build an explicative model for this system. So we're looking for a model, right? But are still interested in predicting what may occur. How can we resolve this difficulty, right? So we come up a with a empirical model, right? Because you solely have just a data point. What are you going to do is that either you can use curve fitting or interpolating with higher order polynomial functions to predict the amount of elapsed time of a tape recorder as a function of its counter reading. So let's C sub I represent the counter counter reading, and T sub I is the corresponding amount of elapsed time. Okay, so this is the table of data that they collect at the beginning, right? So what we're gonna do is we're gonna do the divided differences to see should we use polynomial functions or not, and if so, if yes, in what order should the polynomial functions be? Okay, so I'm gonna go to the next tab and then change this to example 3. And I'm just going to copy and paste what I have for the data. So this is the data, similar to what we have here. So you don't have to write the information here in this table. It's just for us to have a as a so this is kind of a placeholder for us. What you can do for the homework is that you can just submit the Excel spreadsheet and you don't have to write all the information on the paper. Right? So here's the calculation for the divided difference. So the first divided difference is equal to the change in y divided by the change in x. And you're just going to track the calculations or the formula down up to this point, right? So that's the first divided difference. The second divided difference is the equal to the change in the first divided difference divided by the interval on which the change taken place. Right, so this, you track that to this point. Okay. And for the third divided differences, right, is equal to the change in the second divided difference divided by the length of in the interval on which the function has taken place. Right. So this is 10 to -7, which is very small in practice. So this go to zero, this you can assume all of this will go to zero, right? So as a matter of fact, to see the zero in this calculation, let me change this to just 4 decimal places. So if you select this column, right click and go to format cells. You change the number to 4 decimal places, right? As you can see, this is give you 0 in the divided differences. All right, so these calculations tell you what? Tell you that the third derivative, right, is equal to 0, and the second derivative is somewhat constant, right? Even though they do not exactly equal to one another, they are approximately equal to one another. They are close enough to one another to be considered constant, or the changes in this number are very small, right? So that's the conclusions that we can draw from this particular calculations. So the second divided differences are essentially constant. So the second divided differences are essentially constant. And the third divided difference are 0 to 4 decimal places. Right. And because of these two conclusions, is meant that the table suggests the data are essentially quadratic. So the table suggests the data are essentially quadratic, right, which supports the use of quadratic polynomial functions as an empirical model. Right. So from this data set, we say that, okay, yes, we should use polynomial functions, and the order or the degree of the polynomial function is of degree 2. Right, so that's for example 3. Now let's move on to example 4. So in this example 4, we have a table of data that reflects a vehicle's total stopping distance as a function of its speed, right? So here's the table of data that we collect, and we're going to do the calculate. We're going to calculate the divided differences. Again, to see if we should use a polynomial functions or not, and if so, if yes, what is the order or what is the degree of the polynomial functions that we need to consider. So let me go to the Excel file again. So here is the data that we have for our example. Now we're going to calculate the divided differences and see what kind of polynomial functions we should use. So the first divided difference is going to be, so it's going to be the change in y divided by the change in x. And then you drag the formula down. The second divided difference is going to be equal to the change in the first divided difference divided by the change or the length of the interval on which the change has taken place. I track the formula down. Now for the third divided difference, you have this is equal to the change in the second divided difference divided by the length on which the functions or the change has taken place. So as you notice, there's some negative occur in our calculations. Right. So let's change this into just 4 decimal places. It's easier to see. So select this information, right click, go to format cells and hit number, change that to 4 decimal places. And you can see it's a lot better to look at. And so the changes in the divided difference, the third divided difference already is small, right? Or essentially constant. So you can also suggest that you can use these quadratic functions or the polynomial functions of degree 2. Now for the fourth divided difference, so let's see. So the fourth divided difference is the change in the third divided difference divided by the length of the interval on which the change has taken place. So drag this information down and change this column to just 4 decimal place. All right. So doing this calculations give me a few idea here. So because the change in the third divided difference are essentially small, you can suggest the use of polynomial function of degree 3, of degree 2. Also, at the same time, you recognize that there is still some differences in the fourth degree in the four divided differences. So it suggests that a use of polynomial function of degree 3 is still good. Or rather is a better approximation for this particular data set. Okay, so that's the conclusions that we want to draw here. So the third divided difference are small in magnitude compared to the data. Right, so essentially this can be for support quadratic function or a cubic function. All right. The negative that you see in the calculations, the negative signs have begun to appear. Indicating the presence of measurement errors. Right. And if you continue doing this, however, if you continue doing divided differences, however, uh, you will see that there are some oscillations in the divided differences, right? It changes from positive, and negative, and so on. And because of that, you expect to see some sensitivity to the data error because you have some measurement error occur when you collect the data. So you have to be careful when you come up with, when you do the calculation, and you need to stop at certain point. If you move too far away or you calculate so many divided differences, you will see there's some oscillation and some sensitivity to data errors. Okay, so additions of high order. Higher order terms increases the complexity of the model. Right, so it's not always the higher degree, the better, right? So it depends on the data sets that you have. Right, so because two things that may happen is susceptible to oscillations and is sensitive to error, to data error. Okay, so yes, in this case, in this particular example, we still use the second, we can still do divide differences and propose a polynomial function of degree 2 or the polynomial function of degree 3. If you continue doing the key calculations for divided differences, you may you may encounter some complexity of the model, again, susceptible to oscillation because you have negative in your calculations. And because of that, it's sensitive to the data error to occur in the process of collecting data. Okay, so now let's go to the last example in this lecture. So you have seen this example already in lecture 3, in lecture 2 and lecture 3, when you look at the biomass growth of a yeast culture and you come up with the discrete logistic growth model. And so we know that for a fact that from this data set, you plot the data set and it behave like a discrete or a logistic growth model. But still, for the insanity of this divided difference calculations, what we're going to do is we're going to do a quick calculation and see what's going to happen, right? So let me go to the Excel spreadsheet again. So let me change this to example 4. We go to the next tab and change that to example 5. And I'm going to copy and paste what I have for the data set. Right, so we have 2 columns of data here. So one is for time in hours and one for the yeast biomass. Now do the divided differences. So the first divided difference is equal to the change in y divided by the change in x. You track the calculations down. Now the second divided difference is equal to the change in the first divided difference divided by the length of the interval on which the change have taken place. The third divided difference is equal to the change in the second divided difference divided by the interval on which or divided by the length of the interval on which the change has taken place. Let me make sure that I'm doing this correctly. All right, so let's change the decimal place to 2 decimal places. It's easier for us to see. So that is the case. Divided difference, the fourth divided difference is equal to the change in the third divided differences divided by the length of the interval on which the functions, the change has taken place. And also we're going to change this to 2 decimal place. Okay, so through this calculation, you can see that it's not a good thing to consider a polynomial function to fit this particular data set because there's a lot of oscillations, right? So it's alternating between negative, positive, negative, positive, negative, positive, and the number change rather drastically compared to all the example, because now remember this lecture is for low order polynomial functions. Now up to the fourth divided difference, you still see a lot of differences in the number, right? So you can automatically from this calculation, you can say that, okay, this is not a good model to, so polynomial function could not be a good model to fit into this data set, right? So obviously, if you try a quadratic function, this model, this quadratic does not fit very well with the data that you obtain from the observations, right? So you automatically can conclude that do not choose polynomial functions and move on to another move on to another model. Okay, so that's it for me for this lecture. So in this lecture, we investigate divided differences. Another name for that is the Newton's divided differences, and to help us identify if the data set suggests a good polynomial function or not. If you want to use a polynomial functions, what order should we consider for the polynomial functions? All right, so that's it for me. Please let me know if you have any questions. Thank you.